So I welcome all of you to my to the first class of BSM 301, and I'm going to start officially my today's session. The session is being recorded. So first of all, I hope that you have gone through the syllabus once. I shall upload the syllabus in the Google Classroom too later on. By this weekend, I am going to do this because, as I told you, that I would be posting the course file, which gives you the bird's eye view or a glimpse of what is going to be done. A course file is a kind of trailer of a movie. So from this course file, you will get to know that what we are going to study and how we are going to study. So the previous course file had some difficulties in it, which is rectified. And by the way, we will finish writing the course. Teachers are taking BSM 301 in two different, and therefore both of us together are working on it. And by tomorrow, you are going to get the course file. Once you get the course file in the Google Classroom, then I ask all of you to go through the course file just like a person reads the research paper. You go through the course file, you will get a glimpse of what is going to be done and how it is going to be done. And in the course file, you are a part of the course file is about the syllabus, okay, and my lesson plan, how I'm going to take the class. We are going to take the class, so you can correlate the syllabus with the lesson plan prepared by the teachers. So everything you will be getting by this weekend. So I think that probably you have gone to the course file by downloading it from university website, and you know what is there. There are 6 modules in the course curriculum. The first module is about the basic probability, and that I'm going to start today. Now, without giving the introduction of the course, if I start solving the mathematics, I mean, that is not a kind of thing that you want. First of all, a brief introduction of probability. You know probability very well. You have done the probability in your school days. In CBSE curriculum and ICSE curriculum, to some extent, probability theories are there. But the approach of the probability that I'm going to deal with in this particular class will be different from the previous approach. So what is the difference that I'm going to tell you? While dealing with probability, there are 2 questions which are always in front of us. First question is, why probability theory? Why do we need probability theory? And how to deal with the probability theory? Now, the answer to the first question is, probability theory is used to study the randomness of the system. It is a kind of quantification of our lack of knowledge about the system. And the answer to the second question, that how to deal with the probability, is there are some basic rules which needs to be satisfied, and with the help of which we are going to deal with the probability theory. These basic tools are kind of some properties which are only valid inside a mathematical space. If you go beyond the mathematical space, these properties actually violate. They do not work. As long as you are there inside the mathematical space, these properties will work. What do we mean by that? A student is going to a disco pub, and after reaching there, he starts solving mathematics. That student will be humiliated. Okay, he will be laughed at. The people will say that he is erratic, eccentric. The same student, when comes to classroom, and here if he starts dancing, he will be punished. So in one physical system, he is going to be humiliated. In another physical system, he is going to be punished. Why? Because he has just reversed the properties of the system. Physical system of disco and pub is guided by some rules. Physical system of classroom is guided by some rules. And you have to, any person belonging to that particular system has to satisfy that set of rules. So from pedagogical point of view, that disco pub is a kind of space in which some properties are defined. You have to follow. Classroom is a kind of space in which some properties are defined that you have to follow. And these spaces are actually, we can say that they are guided by different set of properties or rules. Likewise, here we are going to talk about a mathematical space where some mathematics property or mathematical properties are there, and probability, if you want to deal with it, you have to consider those properties and you have to work on that. Okay, so this is the thing that I'm going to talk about. Now, these properties are actually called mathematically, the properties which the probability theory is based upon is actually called axiom. Axiom is a kind of rule or a set of rules which cannot be proved but only can be tested in the with respect to the context of the situation which is in our hand. So that context which I'm going to discuss right now in today's class, that what are these axioms and how to deal with that. This approach is called the axiomatic approach to probability. Okay, so I'm going to share a whiteboard with you, and I hope you all of you will be able to see the white screen. And just a minute. Yeah, so I hope all of you can see my white screen, and whenever it is required, I'm going to write on that. I'm not writing anything on the whiteboard screen now. First of all, let me prepare the premise of the discussion. Before I start finding the probability of something, probability of the event, what we need is called the sample space. And you know, the sample space is the set of all possible outcomes. Okay, so we need a sample space. You know very well what is the definition of sample space. I'm not writing the definition. Only the important part is that we need, in the sample space, it contains all possible outcomes, a set of all possible outcomes. Whenever the sky is cloudy, it doesn't always mean that there will be rain. For rain, some other parameters are there which needs to be satisfied. Some other parameters which are known to the meteorologists. Okay, general public, we do not know about this. They study those parameters and they say that there will be torrential rain, there will be heavy rain, just not because of the cloudiness of the system. So suppose you have all the information about the parameters which define rain. In that case, you can say that there will be raining tomorrow or day after tomorrow, heavy thunderstorm, and so on and so on. So if you consider all the parameters which define rain in a particular set, that collection will be called sample space. Now think of a part of that sample space which define not rain, but only the humidity of the weather. That part is a subset of the sample space. Okay, so I'm talking about the sample space, which is a collection of all possible outcomes. That sample space actually defines raining. Here, various parameters are there. These parameters must be satisfied. If all the parameters are satisfied, there will be raining. I am now considering a part of this particular set. This is the part, only 3 parameters, as you can see. This part is a subset. If I consider the entire set, if I denote the entire set by capital S, this subset of S can be denoted by capital A. This entire set defines raining. This subset defines humidity of the weather. Okay, now this particular subset, which is the subset of the entire sample space, is called the event. So the definition of event is subset capital A of capital S is actually called event. So event is also a collection of some sort of parameters taken from the sample space. Okay, and we are interested in finding the probability of this event. We want to find that what we denote by probability of capital A. So whenever we say that we find the probability of this subset, for which is called the event. Now onwards, we are going to call this subset as event. We need some basic rules inside the probability space. So whatever we will be doing over here, we will remain inside this probability space. Probability space has a mathematical definition also. I could have defined probability space mathematically, but if I do so, all the students will lose interest. But whenever I'll send you the note, in the note, the mathematical approach of defining probability space will be reflected. But right now, from the pedagogical point of view, I have tried to make the things lucid for all of you to understand properly well, because this intelligence of all the students vary, and therefore I have to give the structure, I have to place the system or the structure in front of you in such a way so that everybody can understand. So whatever have I said? I said that whenever we will say that capital A is an event and we are going to define some sort of probability on it, that means we are actually interested in finding the probability of the subset of the sample space. But before we do that, we need some basic rules. Another question comes to the mind: why do we need the rules? We could have done the probability problems when we were in school by using the classical definition of probability. So what is wrong with that? If I say that what will be the probability that there will be rain tomorrow, or there will be heavy thunderstorm tomorrow, or the weather will be humid? Okay, by classical definition of probability, you will not be able to, calculate the probability, even if you know the entire sample space. Why? Because in classical probability, you already have assumed something which is very important, and that something is, in classical probability, we consider that all the outcomes or all the elements of the event, they are equally probable. Keeping this in mind, we calculate, or we use the classical definition of probability. But this is not the case. The air quality index, the humidity, cloudiness, all these parameters are not equally probable. So we will not be able to apply classical definition over there. A student sitting for the examination, whether he passes or fails, not equally probable. We will not be able to apply classical definition. So we need something else. Classical definition collapses here. So to deal with such a situation, we need an approach of probability, which is called axiomatic approach to probability. So our first topic of today's class is axiomatic approach to probability. Whatever I write on the board, you just copy it. Later you will be getting the note, books, everything. But right now, whatever I write on the board, date-wise you copy it, so that you can keep track of what has been done in the class. There are 3 axioms which needs to be satisfied. Number 1, number 2, and number 3. Carefully listen to me. Okay, I am now just building the premise of our study. First property is that we have an event capital A. By now, you already know what we mean by event. If we define probability on it, or if you want to calculate the probability of this event, we have to keep in mind that this probability must always be non-negative. So probability cannot be negative. This is the first axiom. This axiom is already known to you, but only thing you didn't know that it is a part of the axiomatic set of rules. We have the sample space capital S, the total outcomes, a set of collection of total outcomes. If you want to apply probability on this has to be equal to 1. This is the second axiom, which needs to be satisfied to deal with probability. Third axiom is the following. Before I write the third axiom, a quick prerequisite. Suppose we have two sets. Now I'm talking about sets. Suppose we have two sets, capital A and capital B. Whenever I say that either an element belongs to set A or in set B or in both, we try to express this particular statement mathematically by the notation A union B. From the probabilities perspective, we say that either the event A is happening or event B is happening or both. So this is the notation for either or both. Okay. By keeping this in mind, I'm going to write my third axiom, which is very important. Suppose we have a sample space capital S, and inside the sample space, we have several events like this. What are the characteristics of these events? Suppose there are n events. What are the characteristics of these events? All these events are mutually exclusive. Mutually exclusive means the events are disjoint. With respect to set theory, we can say that there are no common elements. With respect to probability theory, we can say that these events will not happen simultaneously. If one happens, the other will not happen. So they are mutually exclusive. If the scenario is like this, then the probability that either A1 will happen or A2 will happen or AN will happen, this is what we write very in a simple way like this. Union I goes from 1 to n, probability of this union is equal to probability of A1 plus probability of A2 plus probability of AN, which in a short form we can write as the following. So probability that either A1 will happen or A2 will happen or AN will happen or all of them can happen. This cannot be. Both part is missing from here because they are mutually exclusive. Either this or this or this, the probability of that will be equal to sum of their individual probabilities. Okay. So these are the three axioms, simple axioms on which the probability theory is based. If you remove any of these theorems, any of these axioms from the picture forcefully, entire probability theory will collapse. Okay, you cannot proceed to the next phase until you consider all of these axioms together. So in my today's introductory session, this is the first thing that I needed to explain to all of you. So this is the first part, which is very important. Second part is far more important than the first one and pretty interesting also. I'm going to the next page. You can take the screenshot also if you want. Okay. When in school days, we were taught probability, calculating probability using classical definition. Always the teacher started with the problem of coin tossing. Okay. This is the first class probably that you are actually attending where I have not uttered the word of coin tossing initially, but now I'm going to do it because of some reason, because this coin tossing problem is very familiar to all of us. And you can say that this card throwing, this coin tossing, this dice throwing, this gambling sort of things are the premises on for which the probability theory has been developed by various mathematicians. But here I'm not going to talk about these things in details. My objective is something very different and interesting. You carefully listen to me. Every teacher likes to ask the student this particular question. Every teacher. Since during my past 14 years, I have seen that whenever a person wants to talk about probability, always starts with the coin tossing problem. I do not want to break the rule. Okay, so let me ask the question to all of you. And you know the answer very well. What is the probability of getting head when we toss an unbiased coin? We all know that the answer is half. I'm not waiting for the answer, it is half. If I say what is the probability of getting tail, it is also half. You are applying the classical definition of probability, and you are automatically assuming that this head and this tail, they are equally probable. But I have a question to all of you, to those persons. How you are defining that the coin is unbiased? How do you know that the coin is unbiased? So my question is, how can one justify the coin is unbiased? This is my first question. My second question is, if the coin is biased and it is known to us somehow, if the coin is biased, what is the probability of getting head? These are the two fundamental questions which I want to reflect on. Let's talk about the second question first of all. In physical system, in real life, not all the situations are unbiased. Biasedness is kind of, when we talk, we utter the word biased, actually we are saying that here the randomness is present. And when we say that the thing is unbiased, I'm not considering the randomness of the system, but the system, physical situation, real life are all randoms. They are of random nature. So if the coin is biased, and if you want to calculate the probability of head, the answer will not be half. We all know that, because in a biased coin, head and tail are not equally probable. I'm not giving you the reply to this question right now, but at least I can say that classical definition fails over here. Classical definition cannot help. And you know what I mean by this. Okay. So how can we deal with this kind of physical situation where the coin is not biased, not unbiased? Probably axiomatic approach of probability can help us in this regard. So this is the first thing that I wanted to explain to all of you. The first fundamental question is, how can one justify that the coin is unbiased? Answer is no mathematical algorithm or experimental process are available. No mathematical algorithm or experimental process are available. We cannot justify whether the coin is biased or unbiased by any mathematical algorithm or experimental process. But here, one particular way that can help us in this regard, and that is called the statistical process. Statistical process with respect to the probability theory, which probably can help answer to this question. Right now, I'm not going into the details of this statistical process. This will be discussed in module 5 of your syllabus. The answer lies in the chapters of module 5. When we will start this module 5, we will discuss this particular question. How by using the statistical process, we can justify that the coin is unbiased. But no mathematical algorithm is available, no experimental process is available. So keep this in mind. When we like to ask this question to a student, what is the probability of getting head? This is a very symplectic situation, which doesn't often happen in real life world. Okay, so none of you probably have thought about this particular question that I have raised so far. And this is the most important thing for which the probability theory has been developed. This is the premise. But you will be getting the answer to the second question in today's class. But before that, we have to deal with a bit of mathematics. Or you can say, I'm going to show you certain problems which can be dealt with the help of the axioms. Now, you know that axioms are the properties or characteristics which cannot be proved. They can only be tested with respect to the context. But there are certain properties which can be proved with the help of the axioms. And whatever I'm going to do right now and in my subsequent classes, all I'm doing inside by keeping myself inside the probability space, by considering all these three axioms together. First of all, I'm going to write these properties one after another so that you can quickly copy it. And then I'm going to prove or show you the way by which these properties can be proved with the help of axioms. So my first property is, quickly you write, probability of phi is equal to 0. Phi is the notation. Phi is the notation for defining impossible event, any impossible event. My second property is probability of A plus probability of A bar is equal to 1. This is not axiom. This is a, you can say that these are the theorems. Let us call them theorems. A bar is complementary event to A. Complementary event to A. That is, A bar implies A is not happening. Number 3 is, if capital A, or let us write it in this manner, so capital B is subset of capital A. By this I mean B is the sub-event of A. What do you mean by this? This means, suppose we have the sample space capital S. Inside it, we have the sub-event capital A. And inside the sub-event capital A, another sub-event is there, which is B. Then probability of B is less than or equal to probability of A. Number 4 property is probability of A will lie between 0 and 1. All these things are known to us. And the last one is probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. These theorems can be proved using the axioms which we have assumed so far to study the probability theory. Okay. Let me save the chat, otherwise I will lose it. Okay. Now I'm going to start discussing about this proofs of this some of these theorems, but probably I'll not be able to finish it in this particular session. I have to carry it forward to the next session. You quickly copy these things, or you take the screenshot of this particular page, because you can see that the time remaining is 3 minutes 42 seconds. So let us begin. Let me see how much I can do in this particular session about these theorems. First theorem is probability of phi is equal to 0. Here phi is defines any impossible event, a general notation to define impossible event. We want to prove it with the help of the axiom. So how can we prove it? Just see the approach by which I am going to show it to you. Proof of 1. Capital S is the sample space and phi is the impossible event. Capital S is the total event which can happen. Phi is the impossible event which can never happen. And you know that if I take this union of these two, that either all the events or any of the events can happen or none of the events can happen, this is simply equal to capital S, because S union phi is equal to capital S. Probability of S union phi, if I apply probability on both sides, we will get this. S phi are disjoint. It is quite obvious. And since they are disjoint, I can apply the axiom 3 over there. So we can write it as probability of S plus probability of phi is equal to probability of S. And you know that probability of S is a number which is equal to 1. Probability of S is a number which is equal to 1. We can cancel both probabilities on the left hand side and on the right hand side, and we get probability of phi equal to 0. A very simple approach that has been followed over here, and which can prove that probability of any impossible event is 0. Okay. Number 2, capital A is the event which happens. A bar is the event which cannot happen. You know that both of them are mutually exclusive. And I'm assuming, for the sake of my problem, that capital A is the only event present inside capital S. Only event. Outside event is capital A bar. So that their union is capital S. If I apply probability on both sides, again we can apply axiom 3 because they are mutually exclusive. And which proves the second property very easily with the help of the axioms. Okay, this much at this point I'm actually stopping, because this particular session is going to be disconnected. In the next session, I'm going to continue with my discussion on this particular theorems. Okay, so join in the next session. There will be 2 sessions per day.